So what the fundamental theorem is about, hopefully you said something like this. There are two ways to express an amount of change of a quantity, or the net change, or the net accumulation. There's two ways to express that. Okay? You can express it in open form with the rate function. That's our integral. Right? So the left side there, what is that saying? That's saying the net accumulation starting at C to some variable endpoint x for some quantity whose rate of change is r. Okay? The other way to express, so this would be r sub f. The other way to express that net change would be the final amount of the quantity minus the initial amount. Right? So how are f and r sub f related? How are f and r sub f related? What is f and what is r sub f? Yeah. Right, so f is accumulation function or amount function, where r sub f is this exact rate of change. Okay? And so this is, again, the total change in the quantity. You can do final value of the quantity minus initial value. Or you can write it in open form if you have the rate function, and it's the net accumulation by adding up little bits of accumulation, and each little bit would be the rate times the little change in x, and then we're summing all those up. Two ways to express a net amount of accumulation for some quantity. Okay, and then what we saw was, one use of the fundamental theorem was writing these open, so this is an open form net accumulation. We can use the fundamental theorem to figure out a closed form of that open form net accumulation function. We just have to have the accumulation function whose rate is that. Okay, so let's do one more example. So here is a accumulation function. Maybe it's a total amount function, sine 4x. And we know if the function is sine 4x, then the rate of change is? This is a chain rule, right? This is a nice easy one. Cosine 4x and then times the rate of change of the interior, which is 4. So we got 4 cosine 4x. So by finding that rate of change function, it allows us to now we can write a closed form of this accumulation function, which is the accumulation from pi over 3 to x at the rate 4 cosine 4t. So here's your chance. So I want you to write this accumulation function shown in open form. You can now write it in closed form if you're following what's going on. So go for it. Write that in closed form. Where's Ryu? Sue? Did you get it? Tell me. Okay, so try me one more time. Okay. Not quite. So what are we doing here? So we're saying that we could rewrite this as, so just before you do any sines or cosines, how could you start? What could you say? That this is equal to what before you use cosines or sines? Okay, there we go. So f of x minus, so it's going to be final value of the quantity minus initial. right? The change is final minus initial. So then I think here you got sidetracked. What is f of x? Okay, good. All right, and then f of pi over 3 would be what you got when you plug pi over 3 into that. So I think this first step is really helpful, okay? So start by writing this first step. Okay, so that's going to be sine 4x minus sine of 4 pi over 3. And so now we have a closed form accumulation function for this open form accumulation function. Okay, so what is the relationship between those two functions? Yes, that is the rate of change of this, right? So that's the rate of change of this. But in a more mechanical sense, a more mathematical sense, what is the relationship between those two? What is 4 cosine 4t relative to this accumulation function that we got? Think mastery test, right? Isn't this the derivative of this one? Right? If this is the rate of change of this function, then it's the derivative of this function. Okay? So then what does that make this function relative to that? Yes, this is what we call antiderivative. Okay? It's not opposed to derivatives. It's not a political statement. Okay? But antiderivative means that it's the function whose derivative is the one you started with, right? So an antiderivative is simply the function whose derivative is the one you started with. Okay, so consider the rate function given below, all right? Describe the meaning of this expression, then find a closed form equivalent. So find the closed form of this expression. Go, find the closed form. So in order to do that, what do you need? What do you need in order to do that? Yeah. Well, that is the accumulation function, right? That is an open form accumulation function. So, yeah. So, what do you mean?
Well, like the accumulation of the rate of change.
Okay. All right. That's still one form of that. So you're talking about a closed form, right?
Yeah, close.
Okay. So and what is that? We just talked about that. Do we need the derivative of this? We need the antiderivative, right? We need a function whose derivative is this one. So this is like so here we didn't start with some function, find its rate, and then set this up. Now we just have this open form accumulation function, and we got to figure out what we need a closed form. And so to find that closed form, we need the function whose derivative is this. Or in other words, we need the antiderivative. And that's a nice easy one. So you think about the mastery test. What function, if I took the derivative of it, would give me 3t squared? You all should know, right? What is it? X cubed, right? X cubed. So it's going to be x cubed. Is that it? Minus 1 cubed. Or x cubed minus 1. So this is the idea of antiderivative. What function would have the derivative of the given function, right? The given function 3t 3xt squared. That's a derivative. What function has that as its derivative? X cubed. In this case, yeah, x cubed. And so then to get this amount of net change, we need x cubed minus 1 cubed. Okay, so x cubed minus 1 is an antiderivative of 3x squared because, so yeah, so what's the derivative then? Derivative of this is 3x squared. Okay, do this one. So write this one in closed form. Where's Khalil? Khalil here? How about Randall Michaels? Randall, how'd you do? I'm gonna write it this way, is that okay? Yeah, you simplified it, that's fine. Okay, and so then that turns out to be x cubed. Now let's simplify. Plus 8, right? Okay, what's the derivative of that? 3x squared. This one. X cubed minus pi minus 1 cubed. Derivative of that is? Okay, so given some function, how many antiderivatives does it have? Yeah, so there's lots of there's many antiderivatives. Given a function has many antiderivatives. Given a function, how many derivatives does it have? 1, right? So function only has, so that's the mastery test. Given a function, it only has, there was one right answer to get that right. There was one right answer. That was the rate of change function, the derivative. But given a function, it has many antiderivatives. Because any of these all these functions and many more have the derivative, 3x squared. Therefore, they're all antiderivatives. Okay, so if g is the derivative of f, then f is called an antiderivative of g. Right, so the derivative of f is the rate of change of f with respect to x. The antiderivative, or an antiderivative of the rate of change is f again. So every accumulation function is an antiderivative of its rate of change function. That's what we just said. Okay, but every rate of change function has more than one antiderivative. So that's a summary of what we just talked about. Oh, this is the slide I wanted before. Okay, so here's this. This is the same ones we did before. So every rate of change function has more than one antiderivative. So the improper integral, so without bounds here, notice now we've always had a starting value and an ending value. If you don't have that, that's what's called an improper integral. Improper integral. Okay? No, indefinite, right? Right. Sorry. That's not improper. Improper integral is something else. This is an indefinite integral. Right? Because so when it has bounds, it's definite, right? So we know where we're starting and ending. If it's an indefinite integral, is when you don't see any bounds. So what does it represent? It represents all antiderivatives of 3x squared. So here we had what? X cubed minus 1. Here we had x cubed plus 8. Here we had x cubed minus pi minus 1 cubed. And there are many more. There are many more antiderivatives. So the indefinite integral without any bounds represents all possible antiderivatives. So what forms do those take on? They all take on the form, what? X cubed minus a cubed, whatever that a cubed was. So whatever that starting value of a was. So all antiderivatives take on this form x cubed minus a cubed. And so really that minus a cubed, that's just some constant. And we know that if you take the derivative of x cubed plus any constant, you're always going to get 3x squared. So all indefinite integrals, 3x squared, have this form, x cubed plus c. And that plus c is what? That plus c is minus a cubed in this case. Minus a cubed. Subtracting off what? The accumulation at the starting point. Okay, so in general, the indefinite integral is f of x minus f of a. And that minus f of a is just a constant, so we could rewrite it as plus c. We could rewrite it as plus c, any constant. And then that gives us all antiderivatives of the rate function, r sub f. Okay, any questions on that? All right, so remember our friend there. Where is it? Okay, we can do this now. Here we go. Okay, so let's do this, making sense of more complex expressions. How about this? So what is this? D dx of the integral from 4 to 7 sine 3 cosine x dx. So this is more complicated. We got lots of notation flying around here. So we want to start by really thinking about what does it mean, okay? What does it mean? And when we think about what does it mean, we want to kind of work from the inside out. Kind of work from the inside out. So why don't you take a minute to talk with the person next to you and make sense of this expression. What does it mean? Before we do any computing or rearranging, what does it mean at face value? Okay, so why don't you talk to the person next to you. Go. Okay, write it down, or I've got it on the board. Just keep talking about it. So after you think you understand what it means, then maybe you start to chisel at how would you, quote, solve it, or what would you do, okay? So I need to find something. So keep working on it. Okay, how'd we do? So I gave you the kind of the guidance to work from the inside out. So let's just look at, so first of all, let's look here. What is sine of 3 cosine x? What is that? It's a rate of change function. Okay, we got a rate of change function. What is, I heard you. It was perfect. What is the integral from 4 to 7 of sine 3 cosine x? So now let me put a blue box around that. So who can tell me what that means? Just what I put a blue box around. Yes, sir? No, what does it mean? That you're trying to solve something. Okay. 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 Good. It's the sum of lots of little bits of accumulation according to this rate from 4 to 7, which makes up what? Then gives us what? A total amount of change, right? A total amount of change. Is that thing in the blue box? What is that? Is that a function? Is it just an expression? Is it a value? What is that? Do you get something as a function of x from that, or do you get an actual number from that? You get an actual number. That's an amount of accumulation at that rate, starting at 4, ending at 7. That is a particular value. So that is a number, a value. And then in the red box, what are we doing then? We're going to take the derivative, or the rate of change, of what's in the blue box. What is it? Did you get it before we started talking again? It's 0, because it's the rate of change of this expression, which is just a number. It's just an amount of accumulation. So really nice question to see if you understand what things mean. Okay? So wait, someone said, did you get what happened? Did you see it? It's all about knowing, being very confident about what this is right here. What is that? That's an amount of accumulation. It's a net amount of accumulation starting at 4, ending at 7 at that rate. Okay, if you're talking about math, that's great. Just whisper. Okay? And so what I put in the blue box there is, okay, we ready to focus back in? Okay, so this is the rate of change. This is an amount of accumulation. So this is a number. It's a constant value. It's not a function. How would it be a function? It would be a function. What we've been used to is if this 7 was allowed to change, right? We wouldn't want to use x here. If we got x's here, we'd need something else, like u or something. But if that's allowed to change, then it's a net accumulation function. But with a 7 there, this is a particular amount, a constant value of a net accumulation. And so now what happens when you take the derivative of a constant? 0. Derivative of a constant is 0. Okay, so now here's another question. So now we've got an accumulation function. Now we've got an accumulation function. And so before we get to the derivative of it, so can we make sense of this or go somewhere with this? Well, what do we need? We would need, if we want to use the fundamental theorem to write this in closed form, we need an antiderivative of sine of 3 cosine t. Okay, well, what's that? What function has the derivative sine of 3 cosine t? Apparently, it's not immediately clear. We could try some stuff, but it's We could try what? We could try like a negative cosine of 3 cosine t, but would that work? So, because by the chain rule, we'd have to, if we took the derivative of this, the chain rule would give us another term to multiply on, which we don't have over here. So that doesn't work. Okay, so what we're going to do is, we don't have, there's not an apparent antiderivative that we can just write down, a closed form antiderivative. So let's just let capital F of x be an antiderivative of that rate function. So we're just going to, so we can let f of x be an antiderivative of sine of 3 cosine t. And now we can make some progress. What does that thing in the blue box equal then? What does that thing in the blue box equal if capital F is an antiderivative of sine 3 cosine t? Now we can apply the fundamental theorem. F of x minus f of 4. Does it make sense? So we don't know specifically what the rule for capital F is, but we know it's an antiderivative of this function sine of 3 cosine t. And so by the fundamental theorem, we can rewrite this expression as d dx of f of x minus f of 4. Okay, well, how do we take the derivative of a difference? We just do the individual derivatives, right? We like that rule. It's nice and easy. Just do the individual derivatives. Okay? So let's start with this one on the right. What's the derivative of capital F of 4? It's got to be 0 because f of 4 is going to be some numbers. That's 0. And now what's the derivative of capital F? What's the derivative of capital F? Well, what was capital F defined as? Capital F is what? The antiderivative of sine 3 cosine t. So what's the derivative of capital F? Yeah. Yeah. Why does this make sense? Looking back at the original expression. So look at this whole expression. Why does that answer make sense compared to that original expression? Tell the person next to you. You got to make sense of this. So looking at that original expression, that answer should make perfect sense. Why? What? Thanks. This should be x. Thank you. Okay. So what's in the blue box there? What kind of function is that? Net accumulation, and we know its rate of change, right? Its rate of change of this accumulation function is sine 3 cosine t. And what are we going to do to that accumulation function? Find the rate of, take the derivative, or find the rate of change of that accumulation function. Well, that's sine 3 cosine t, or sine 3 cosine x, okay? So that makes sense. But this process that I just went through, you need this process because we're about to do one where you can't just always just take that rate function and write it down, okay? So yes, it should make sense that the rate of change of an accumulation function with this rate of change will be that rate of change, okay? But let's look at another example where you need this process that we slowly walk through. You got to have that. So let's do that. Okay, so we did all that. No, not that one. This one. Okay? So I'm going to tell you right now. This one, so this is, again, this is a rate of change of an accumulation function. And we have a rate of change function here, 1 plus w squared. But I'll just tell you right off the bat, the answer to this is not the square root of 1 plus x squared. Okay? Something else is going on here. Something else is going on. You need that process that we just walked through to solve this. So, see if you can do it. So we're gonna start by saying what? And again, this right here, this does not have a straightforward, nice, easy, closed form antiderivative. Okay, so it would if we had a w out here. If we had a w to the first, then you might see that it's kind of the result of a chain rule derivative. But there's no w out here. So because of that, this does not have an immediately apparent closed form antiderivative. So we're going to start by, we'll get you started, and then you can take off from there. Let's call it capital G this time. Let capital G be an antiderivative of square root of 1 plus x squared. No, x squared, because it's g of x. Right? G of x. Okay, see what you can do on this one now. Okay, so what should it be? So this, now we can rewrite this accumulation function as, if g is an antiderivative of radical 1 plus x squared, then this accumulation function can be written as g of e to the 4x minus net change, right? Net change so we know the derivative of g to the negative 5 is going to be 0. So what we're left with is the derivative of g e to the 4x. Who thinks they got it? Yes, sir. Okay. Is that it? Why not? Yeah. So you got the right idea, but remember, it's with respect to, not with respect to the rate of change, but with respect to that first. And then what happens after that? Right, which is what? Okay, so you had the right idea, but you just didn't apply it quite right. Somebody knew. Somebody know that? Are we done? We're not done. Why not? I'm doing the rate of change of g to e to the 4x, right? We know g of x is this, so this is a good start, but we're not done. Yeah. Why would we do that? Yeah, so we're going to have to apply the chain rule here. We're doing a derivative of a composite function, right? This is a derivative of a composite function with e to the 4x plugged into g. So the rate of change will be what? The rate of change of g with respect to e to the 4x, just like you did in the mastery test, right? You're going to write the rate of change of... I didn't do this. Yeah, right, sorry. So the rate of change of g e to the 4x is going to be 1 plus e to the 4x squared, and then times the derivative of the interior function, which is 4e to the 4x. So this is what that expression is equivalent, the rate of change of this particular accumulation function. Right? So this is an accumulation function. The rate of change of that accumulation function is this. Question? 4e to the 4x, because it'd be derivative of e to the 4x would be e to the 4x, then times the derivative of 4x, which is 4. No, not with the e function, not exponential function, just, yeah, not exponential function. All right, question on that? Okay, so you see how that's vastly different than just 1 plus x, radical 1 plus x squared. You've got to work through that process to get this. So, anybody have a question? Did I lose you? So the whole point of this is chain rule. The derivative of a composite function. We know the derivative of g is this 1 plus x squared, yes, but times the derivative of the interior function. It's the chain rule. Any questions? Okay, so there's going to be a short assignment for Friday to get us ready for Friday's class. So there'll be a don't miss that. Short assignment for Friday. Again, this stuff and Friday's class really important for the final.